Hello, I'm Vahin Natevi, and today I'm presenting our work called Autoencoder-Based Thermospheric Density Estimation using GPS tracking data. The work is supervised by Professor Rosenberg. In the presentation, I start with describing the motivations of the work, followed by representing the overall pipeline. Then I discuss the methodology we adopted by explaining a machine learning-based technique for reduced order modeling. After that, the modeling of the thermospheric density field and the overall dynamic model will be discussed. I described the selective estimation algorithm for the density calibration, and before concluding, I will discuss the results we have obtained for the reduced order modeling and eventual density estimation. As everybody here probably knows, we are witnessing an increase in space traffic in low Earth orbit due to, for example, near constellations. Additionally, we know that the dynamics of satellites in LEO are strongly influenced by atmospheric drag at the largest perturbation. So the need for more accurate orbit determination and uncertainty quantification is felt to perform conjunction assessment and collision avoidance maneuver. Considering the existing density model, it becomes necessary to construct a gray box model of the dynamic of density and efficiently perform real-time calibration. Let me explain the whole pipeline of the project. We start with the density field and try to build a reduced order model of the density. Then we use the state-of-the-art method to reconstruct the government differential equations. On the other hand, we have the observed dynamics of the satellites in LEO. Now we can fit our estimator with the models to predict the states. Then by using GPS tracking data, we can have our estimated spacecraft states and reduce order models the state of the density. At the end of the pipeline, the estimated RRM states go inside the decoder to retrieve the density field and then be validated by the true density data. To start our work, we took the density field from the database of high accuracy satellite drag model, HASDEM, which has a temporal resolution of 3 hours and a special grid size of 10 and 15 degrees for latitude and longitude, and 25 km for altitude. In this work, we made use of autoencoders to find the reduced order model of density. Autoencoders are neural networks that are trained such that their input is copied into their output. Based on the usual structure of these neural networks, the inner layers are characterized by a lower number of neurons compared to their input and output. As you can see in the figure, the Z vector, which is associated with the so-called bottleneck of the network, is a compressed representation of the input vector X. If we consider just one layer for the encoder and decoder and use linear regression functions to construct them, we can find a procedure similar to the single value decomposition in which matrices U will arise. To look better, you can see how the density field is compressed and then is coupled with a prediction step to obtain the ordinary differential equation. There is also a work that combines these two steps of compression and prediction in one step, which can be our future work. The prediction step consists of finding the governing equations. We use the sparse identification of nonlinear dynamical systems, SIND, to fit the differential equations governing the spatial and temporal evolution of the density field. Synchronical three-field least square is also used to obtain the symbolic regression. Note that the control inputs such as the space weather and electromagnetic activity have not been considered here. For the measurement field for the estimator, we selected GPS tracking data as GPS receivers are getting popular on the satellites. Specifically for this project, we use GPS tracking data of SWARM A satellite. The data has a frequency of 1 Hz and is available in the SWARM data access as shown on the right. And the measured density by the whole constellation of SWARM is also reported in the same database that are available each 30 seconds. To use the model with the GPS data, we choose Unscented Kalman Filter as we are dealing with a nonlinear problem and we don't want to approach any linearized based algorithms such as the Extended Kalman Filter. So as you can see in the figure, you can try to keep the nonlinearity of the model and propagate the mean as well as the covariance of the states. find the sigma points required in the UPF process, we selected nerve scale sigma points method according to the paper reported here. The sets that we are going to estimate are the modified equilateral elements and the z vector, which is the reduced order model states of the density. We selected modified equilateral elements as they are non-similar and their differential equations are less than linear with respect to the Cartesian coordinates. So Gaussianity is a less stringent assumption. The orbital dynamics we have considered for the satellite consists of geopotential acceleration up to degree and order 48 for harmonics, and the considered perturbations are listed at the bottom of the slide. To initialize the estimator, we need process and measurement noise matrices and initial state covariance. Regarding the process noise, we computed the Q matrix by using the 6-hour prediction on the training data according to the equation in the middle. Z2 is the time series of encoded density field using our encoder, and f of Z1 is a nonlinear function giving the time series of the propagated ROM. For the state covariance, we perform an Unscented transform to convert the state covariance to modified equilateral elements. After training the autoencoder, we reached the encoder and the decoder made of 3 fully connected layers each, and we ended up by 16 for the latent state size. In the figure, you can see the performance of the autoencoder. Here, you can see more detailed information about the training. In the left figure, you can appreciate the overfitting for 1000 epoch training. The final model has been trained for just 300 epochs. Even if we consider 16 components, only 6 are non-zero, and the information is summarized in just 6 of them. The trajectory for 1 year is shown here. And as you can see, there is some correlation between components of Z. It would be interesting to see if this correlation is with F10.7 as well. The history of the encoded Z vector is set into the SIMD, and by using trigonometric functions, we can have our differential equations in the form below. And of course, full expression not written here for the sake of brevity. The result shows that the position and velocity estimation converge quickly. In the middle figure, you can appreciate the position estimation, and in the left and right figures, the 3 sigma of position and velocity errors are depicted. Note that the estimation is performed with the time step of 3 minutes and a whole duration of 8 hours. Here in the left figure, you can see the estimation of non-zero components of this vector, as well as their corresponding uncertainty. In the right figure, you can see the behavior of the Z components with respect to each other during the whole duration of estimation. To touch on what we said at the beginning, we used our decoder to obtain the density using the estimated Z vector. In the figure, you can see the obtained density in blue, 13 average of estimated density in green, and the surround density data interpreted as a true density in orange. It is clear that the estimated density is following the trend of the true density, but with fluctuations. However, you can notice that as time goes on, the fluctuations drop. We run the simulation for 8 hours, and it's reasonable to assume that the fluctuations drop to an accepted range after 1 or 2 days. Note that also in the method, the rates are approximated via finite differencing. That's a linearity assumption that is a source of error for the estimation of Z vector and eventually the density. The non-Gaussianity has a strong implication for the computation of the probability of collision. Since the density appears in the differential equation, the final state is a nonlinear function of a non-Gaussian variable. And existing covariance analysis is much weaker than what we get here in this method. As a conclusion, I can say that autoencoders proved themselves as a promising nonlinear RNN technique. We showed that data-driven techniques can be used to obtain an explicit expression of the system which has a nonlinear governing differential equations. And the result of explicit knowledge of the system lets us perform uncertainty quantification, specifically for the probability of collision in this project.